afternoon. So we'll study with the stress strain curve. So in the stress strain curve, there's an elastic phase where if you're stretching a rubber band or stretching any wire or something. So if you stretch it, it will come back to its original phase. So it is obeying Hooke's law, where your stress is directly proportional to strain. So stress is sigma Newton per meter square. Strain is without dimension. There's no unit here. There's written unit. But strain will not have unit because strain is a change in length divided by original length. So that will have no dimensions. So that's a limit of proportionality where your Hooke's law is being obeyed. After that, till this point where your yield point or elastic limit is there. Here, it is still in the elastic phase, means if you remove the load, it will come back to original shape. But from limits of proportionality to yield point or elastic limit, the stress will not be directly proportional to strain. So in the elastic phase, you have both Hooke's law and not the Hooke's law. So it is following Hooke's law till the limits of proportionality. After that, the stress is not proportional to strain, but if you remove the load in this phase, it will come back to original position. Now after yield point, if you increase your stress, it will be permanently deformed. So the permanent deformation is known as plastic stage. Nothing to do with plastic here. This stage is where it is permanently deformed. You're stretching it more and more. So maximum tensile strength where you're putting is known as UTS. After that, when you reduce your stress, the material is still straining till a point where it breaks on its own or fractures. So that is the break point. Now the area under this curve will determine the toughness of this material. This graph is typically of a ductile material. So this is a graph of a ductile material stress strain curve. It comes in your exam, make the stress strain curve and explain each point. So you have to explain limits of proportionality, you have to explain elastic limit, you have to explain UTS, and you have to explain break point. So limits of proportionality, it is the highest stress prior to which the deformation increased proportionally to the load applied, and beyond which the material will be stretched, but the stress will not be proportional to strain. So it is a greater stress that can be applied to elastic body without causing permanent deformation. Proportionality limit is proportional to the area of cross section. The material type, the loading type will not have any limit or influence on limits of proportionality. That is only dependent on the thickness of the material or the area of cross section. So this is your limits of proportionality. You will have a spring breaking here. So Hooke's law is followed till here. After that, Hooke's law is not followed. Now yield point is the amount of stress in a solid on the onset of permanent deformation. That means after the yield point or elastic limit, the material will be permanently deformed. So it is also known as elastic limit, as your elastic behavior ends and your plastic behavior starts. So within your yield point, if the load is removed, it will come back to the original shape. So here you have A, which is the elastic region, B is the elastic limit, C is the yield point, D is the UTS, and E is the breaking point. Now we come to the next point, which is UTS. So it's a maximum stress that the material can withstand while being stretched or pulled before it fails or breaks. So the definition is the maximum resistance to fracture of a material is UTS. So the equivalence is equal to maximum load that can be carried 1 square inch of cross-sectional area when a load is applied as simple tension. Or it can also be defined as uniaxial stress strain test. So that maximum engineering stress is the uniaxial stress strain test. Now if you see in the diagram, you're stretching this material, so you're coming to the proportional limit, and then stress is not directly proportional to strain. So that is your yield point. It is still in the elastic phase. After that, it enters the plastic phase. You're still stretching it. So from yield point to the breaking to the UTS, this is known as strain hardening, because the material is getting strained. After this necking will take place. See, the neck is being formed here. So from this point till fracture point, the necking will take place, and the neck breaks. That is the fracture. So this is your proportional limit, yield point, UTS, and between yield point and UTS is the strain hardening, and between UTS and fracture point is necking. Now we come to one more definition, which is modulus of elasticity. You've all done this in school. So the measure of stiffness of elastic material It is also known as Young's modulus, which is the ratio of stress to strain. So it's denoted by letter E. That's a constant. It's a measure of stiffness of elastic material. So it is a quantity that measures the object or substance resistance to be deformed elastically when you're applying stress to it. So it can also be defined as the slope of the stress strain curve in the elastic deformation area. So this slope we are talking about. We're talking about this slope, the gradient. If it's a soft material, the gradient will be less. Like a plastic material, then the plastic material graph will be like this, come on top and go down. So the gradient of a plastic material will be very less. But here a ductile material, you're pulling it, the gradient is higher. A brittle material, the gradient will be much higher because it might break at the yield point only. Now if you see this diagram, this is the gradient will be much higher because it might break at the yield point only. Now if you see this diagram, this is the original length of the material, you're pulling it horizontally. So the new length is Ln and the change in length is Ln minus Lo. So the strain is Ln minus Lo, which is delta L divided by the original length Lo. That's the strain. You can also write a new length minus old length divided by old length is the strain. And stress is force per unit area, what you're applying on this pipe to pull it. So Young's modulus is stress by strain. So here stress is force per unit area divided by delta L divided by L. So finally it will come as F into L divided by delta L into area of cross section, or force into length, original length divided by area of cross section into change in length is the Young's modulus. So stress is defined as force per unit area. You can have tensile stress when you're pulling a material or you're stretching a material. If you're compressing a material, that is a compressive stress. And if you're shearing a material, when you're applying shear force, so that is shearing stress. Now, this is your tensional stress. You're pulling that, or tensile stress. So I'll just explain in diagrams of a ship, on point of view of a ship, how the tensile strength is coming up. That is in case of hogging and sagging, and how your shear stress comes up. Now, suppose a vessel is hogging, so the tensile stress is coming here on the deck in hog, and a compressive stress is coming on the bottom plating. This is the compressive stress. Now, where is the shearing stress coming up? When you're loading your vessel. Now, this is a vessel. Now you're loading full here, half here, full here. Now, the thing is, you have two forces coming up here. The gravitational force is pulling down, and here you have a buoyancy force which is pushing it up. Because the buoyancy here will be more than force of gravity, so it's pushing up. Here the gravity is more than buoyancy, it's pushing down. And here you have buoyant force is more than gravity, so it's pushing up. Similarly, pushing down. So your shear force is coming on this bulkhead, and the shear force is acting on this bulkhead. Here, shear force is acting on this bulkhead. The shear force is acting here. It's acting here. It's tending to break this bulkhead. That's why the extra strengthening is taken. So that's why you have to see the shear forces here. So that's the shear force which is coming on your bulkhead here. Shear force bending moment, of course, you'll be doing in stability. I don't have to go too much in detail for that. So shear stress is tending to have adjacent portions of material to slide against each other. So here you have shear stresses where the forces are acting 180 degrees against each other. Now, what is strain? So strain is epsilon, which is change in dimension divided by original length, which is delta L divided by L. So you can take it meter by meter or inch by inch. So when you cut it, you will not have any dimensions. So strain is a physical change in dimension of a specimen which results from applying a load. So here you have a change in length by original length. That's why your strain units are dimensionless. So percentage elongation is strain into 100%. So here you have stress and strain. The stress is force per unit area. Strain is change in length divided by original length. This we have done. Now we'll come to what is Hooke's law. So Robert Hooke had made this law for an elastic body. It was not for a plastic body. For elastic body, the strain is proportional to stress. So when the body changes the shape within elastic limit, the ratio of stress strain remains constant and is equal to E. So if you plot on the graph, it will be a straight line where E is stress per strain. But all materials do not follow your Hooke's law. Rubber is non-Hookean because the elasticity is dependent on stress and sensitivity is dependent to temperature and loading rate. The temperature of material being pumped is increased, it will stretch out. If the loading rate is increased, it will stretch out. So here you are not pulling it. That's why this is known as non-hooking, because it is not following Hooke's law. So now you have stress strain relationships here. You have the UTA, apparent stress and all. We'll not do this. I've already explained this. 5 is your necking phase. 4 is your strain hardening. 4 is your strain hardening and 5 is your necking stage. 3 will be rupture. Now if you compare your various materials, on comparison you can make these diagrams. Here you have a brittle material with a very high gradient. Slope is very high. It's going to break at maybe the limit of proportionality also. Here strong material which is not ductile, it is breaking at the elastic limit. Here is a ductile material which is fracturing after UTS. And here the plastic material is being stretched and the gradient is hardly anything. So the graph under this will be very less. Maximum area will be under ductile. And that's why this material is very tough, because maximum area will be under the stress strain curve of a ductile material. Now here you have stress strain relationships of various materials. Aluminum you can stretch easily, not very tough. It's very soft, so you can pull it. Then you have copper. Mild steel has got more toughness. Then you've got nickel, chromium, molybdenum steel, where you can say it's stainless steel, much more tougher. And then you have hard field steel. And you see that thing is increasing further up. So the UTS is pretty high. That's why this is used in making helmets. This was used in Second World War helmets of those soldiers, because it could take the strain. So that was your stress strain relationship. Now we come to steel. So steel being used on ships, your carbon content should not be more than 0.3. Ideally, it should be 0.15 to 0.3. Second thing, your steel should be such that you can do welding and cutting. It should be ductile. It should be homogeneous composition. That means throughout the steel plate, it should not be thick and thin. It should be homogeneous, so that otherwise you will have weaknesses which can provide fatigue and can have fracture. Yield point should be high and it should be resistant to corrosion. It should be available at reasonable cost because you're doing shipbuilding. Now we start with the types of iron. One is magnetite and one is hematite. Magnetite will not be attracted by magnetite will be attracted by magnet, and hematite will not be attracted by the magnet. So pig iron basically is not iron. It is a byproduct. उसको फिर base बना के अलग types of iron use करते हैं, जैसे cast iron, wrought iron. Pig iron से बनाया जाता है. Pig iron का, but when you load this, you have to be sure that there is no moisture, otherwise explosion हो जाएगा, and it is very unstable. So pig iron जो है, it is intermediate product of iron industry, which is also known as crude iron. So blast furnace में जो smelting होती है iron ore की, वहाँ ये product बनता है. Now it's got very high carbon contents, therefore you can't use this pig iron in the industry. So pig iron has got carbon content of 3.8 to 4.7. Because of that, it becomes very brittle. So you cannot use the pig iron for making anything, but it is only used for making cast iron and wrought iron. This is pig iron. So अगर आप देखो इसकी with layers of coke and limestone. Coke is petroleum coke, not Coca-Cola. Coke is petroleum coke, pet coke, and poured into molds so that you can cast into desired shape. अब जैसे आपके stern frame, इसकी height अभी भी है. Welding इतनी आसान नहीं है. Welding requires special welding rods and all. You can't do cast iron welding with normal welding rods. So special rods are used for this, and strength is high. But cast iron अगर गिरेगा तो it can break, so it is brittle. So it is a group of iron carbon alloys with carbon content greater than 2%. So here you have low melting point, good fluidity, castability, machinability is good. It is resistant to deformation and wear resistance. Cast iron पे इतना जल्दी cylinder heads में use करते हैं, cylinder blocks में use करते हैं, gear box में use करते हैं. Now we come to the next iron, which is wrought iron. So ये melting करने. So once you have the final product, that is very ductile. The cast iron was ductile, was brittle. This is ductile. So it is free from brittleness. So your anchors and cables, you can use it for so many times, but they don't normally break. They can break, ऐसा नहीं है. I lost my anchor also, it broke. But अगर कोई never repaired it, so when we dropped the anchor, we lost the anchor. उसी तरह cable भी ऐसा है. But you have to check in dry dock, everything is right. Links and all are got defects and all, then you have to change. Otherwise, you can use it. So it's an iron alloy which is very low carbon content in contrast to cast iron, which has got carbon between 2 to 4, which makes it very brittle. So here your carbon content is less than 0.08, where your cast iron had 2 to 4%. So it is semi-fused mass of iron with slag inclusions, and the grain resembles wood that is visible, which is edged or bent to the point of failure. So if you cut it, you can see that grains are visible there in wrought iron. So the properties of wrought iron are soft, ductile, magnetic, has high elasticity and tensile strength. It can be heated and reheated and worked into various shapes. But here your carbon content is very low, so you cannot make it hard. You can make it tough, but not hard. Because for hardness, you require some certain amount of carbon content. So your wrought iron can be used for pipe making because it's corrosion resistant, fatigue resistant, better welding and threading qualities. It is used for making bars for stay bolts, engine bolts and rivets because it is corrosion and fatigue resistant. It can be also used for plates. It can also be used for chains and crane hooks. Plus, it is also used for nuts and bolts. That is forging industry. The nuts and bolts are made of wrought iron. So here you have the applications of wrought iron, the fancy gate, the hook, these appliances, the chains, anchor, Eiffel Tower, and the iron pillar in near Qutub Minar. That is all examples of wrought iron. Now we come to the next type is steel. Now steel basically has got carbon. So the shape or the structure of those bonding will make the material either cementite or pearlite. So cementite, when the iron molecules are side by side, the pearl-like appearance will give it the name as pearlite. So cementite basically is iron carbide, Fe3C, and immediate transition metal carbide with formula Fe3C. So it is 6.67 carbon and 93.3% iron. So the structural crystal structure is orthorhombic. I'll not go into details of this because this was in chemistry in class 11. That is your crystal structures. You had carbon atom in between, and at the edges you had iron molecules, iron atoms, sorry. So when the cementite is thermodynamically unstable, it is basically, it changes to pearlite and austenite depending on what kind of heating is done. So there's a temperature in this iron which is known as eutectoid temperature, which is around 723 degrees Celsius. And if you're heating more than that, then how you cool it, that will change the molecular structure of that compound, Fe3C. So eutectoid temperature, the minimum temperature at which a material exists in single solid solution phase, so that your alloying elements are totally soluble in the matrix phase. So that is a minimum temperature. After that, the changes will take place. Now, if you see cementite, the structure is orthorhombic with carbon atom here and followed by 3 atoms of iron. You see the grain-like structure here of the cementite. Now the other structure is pearlite. That is also Fe3, but depending on the heating, the structure will change. So it's in a plane phase. You see the structure here, like pearl-like appearance. So the heat treatment, this stage comes in the iron, in the steel. This two-phase lamellar structure composed of alternating layers of ferrite and cementite, which is shown in steel and cast iron. Now, when you do the heat treatment, it depends if you cool very fast or you do it slow. So when you're doing slow cooling of iron carbon, pearlite forms by eutectoid reaction. When the austenite, that's another form, it cools below 723 degrees Celsius. So you have the structure in certain grades of steel also. So the transformation of pearlite to austenite takes place at lower critical temperatures of 723 degrees Celsius, and the pearlite changes to austenite because of nucleation process. So this is pearlite. Now there's another Fe3C, molecular structure will change due to the heat treatments. So this is known as gamma phase iron or metallic non-magnetic allotrope of iron, or a single solution of iron with alloying element. So in plain carbon steel, austenite exists above the critical eutectoid temperature of 1000 degrees Kelvin or 723 degrees Celsius. So other alloys of steel have different eutectoid temperatures. So austenization means heating the steel to a temperature where it changes the crystal structure from ferrite to austenite. If you see, the structure has changed now. That is a change in structure because of the heat treatment above the eutectoid temperature. अभी 10 मिनट है तो वीडियो दिखाएं, देखते हैं कोई.
Yes. Video tutorial, we're going to be looking at the phase diagram for plain steel And in particular, we're going to be focusing in on what happens when body center cubic steel turns to face center cubic steel. And again, this is information that we can obtain from our phase diagram. Before we look at that particular transformation, let's look at a much larger phase diagram. And whilst this looks more complex, what we have is a lot of similarities to the previous phase diagram that we looked at, which involved lead and tin alloys. So the first point on this diagram that I'd like to draw your attention to is this point here. And what we see at this point here is we see our liquid transforming directly into gamma plus Fe3C. Well, gamma is our FCC steel and Fe3C is iron carbide. And we'll talk about each of those a bit more now. On the far left hand side, we see a region marked gamma austenite. And gamma austenite, as I just mentioned there, is our FCC structure of steel. In addition, we have Fe3C, which is iron carbide, but iron carbide is also referred to as cementite. Now this point here, where we go directly from liquid to a layered solid, is called our eutectic composition, and we've seen this previously. So here we have our eutectic composition. Therefore, when steel has a composition of 4.3% carbon, we have our eutectic composition. At carbon contents of around 4.3%, what we're really referring to is our cast irons. Now, the other point of interest is at much lower carbon contents, and the point of interest is this point here. Now, what we notice happening at this point is we have gamma austenite, the face center cubic steel, transferring directly into alpha steel and Fe3C, cementite or iron carbide. Well, alpha steel or alpha iron is actually our body center cubic structure, and we see a very narrow band here for that particular structure, BCC. Now, the name of BCC iron or steel is called ferrite. So really, alpha is primarily iron, but with a small amount of carbon included. Now, the important thing about this point is it's not a eutectic point because we're not going from liquid to solid. In fact, it's called eutectoid. Now, the big difference here is that eu means easy, tectic means melt. So at our eutectic point, we have the easy melt point, or the melting at the lowest temperature. Eutectoid means easy melt-like. We're going from face center cubic iron or steel into body center cubic. And as we saw in an earlier video, this isn't a change in state, it's a change in solid structure. The last thing to point out before we focus in on this eutectoid point is that cementite is actually a ceramic. It's a very hard, very brittle material. So in effect, we have soft iron combining with very hard cementite. So now let's focus in on our eutectoid point. Okay, so we've already mentioned that austenite or gamma steel is face center cubic. And we've also mentioned that ferrite or alpha iron is body center cubic. Now we have this very narrow band on the left hand side which represents ferrite with a small amount of iron carbide dissolved, or Fe3C. That Fe3C is also known as cementite. So on the left hand side we have BCC iron with a small amount of cementite dissolved. Now, in terms of our other regions, we have alpha plus gamma, which is a mixture of alpha iron, BCC, and gamma austenite, FCC. We also have a region which is cementite, Fe3C, plus gamma. And at the bottom, we have our region, which is alpha plus cementite. This laminated mixture of alpha and iron carbide is also known as perlite. And alpha plus cementite will extend to both sides of our eutectoid point. So the first thing to discuss is what happens at our eutectoid point. Well, at our eutectoid point, we're going to go directly from austenite, FCC, into our laminar layers of alpha plus iron carbide, or ferrite plus cementite. So I'll sketch it up here at the top. At that eutectoid point, we're going to go directly into our layered structure, and those layers will be alpha, ferrite, and cementite, Fe3C. So we have perlite with alternating layers of alpha and the ceramic material iron carbide. So very similar to our eutectic point where we went directly from liquid to solid, here we're going directly from gamma FCC into alpha BCC plus cementite. Now the important things to point out there is that the percentage of carbon is 0.77%, and the transformation is occurring at 727 degrees C. So the lowest temperature, the FCC will go to BCC, or BCC will go to FCC, is 727 degrees. Let's pick another point. This time, let's assume that we have 0.4% carbon steel at a
Okay, then we'll have a tea break.